Dear friends and colleagues, first of all, I would like to thank you all of you to be with us today at these interesting lectures prepared by Rosatom Moscow and our Russian professors from Moscow Engineering and Physics Institute and Tomsk Polytechnic University. You know that the nuclear power industry is a relatively young industry, and it is now dynamically developing all over the world. In the world, there are about 200 nuclear power stations. The majority of them are situated in the 5 top countries. USA producing about 20% of nuclear energy, France producing 70% of nuclear energy, Japan 30% of nuclear energy, Russia 20%, and China, in which is producing 5% of nuclear energy. In comparison, in India is only about 2% of nuclear energy from all consumed energy in the country. And 60% in India of all energy are produced in the coal power plants, which are economically unprofitable and very polluting the atmosphere. Now in India, there are 22 nuclear power units, 2 of which were constructed and put into operation by Russian Atomstroy in 2017 in Kudam, in Tamil Nadu state. India has a big perspective in developing of nuclear power energy, and there is a big need in engineers and scientists in this regard. You must know that the atom is used not only in these purposes, but now is used in the peaceful purposes, in medicine, agriculture, biology, shipbuildings, etc. And you, my dear students, you could become the specialist in nuclear energy and atomic technologies and contribute much to your good and great country. Come to study in our Russian worldwide famous and honored institutes and universities. Thank you for your kind attention. I welcome our Professor Aleksandr Nahaba from MEPhI, Moscow Engineering and Physics Institute. Please.
Thank you very much. Now I'll try to demonstrate my screen. Is it okay?
Yeah.
It's visible?
Yes, visible.
Okay, thank you very much. Let's start. My name is Aleksandr Nahaba from National Research Nuclear University MEPhI, Moscow, Russia. And I'd like to say today about, you see, atoms for peace, technology of the future. Actually, it's a very hard task because I'll try to put in 45 minutes a lot of information, but I hope interesting for you about different applications areas where nuclear and radiation technology can be used nowadays and in near future, first of all. So, first of all, I'd like to start from a little bit physics. Of course, I hope all of you knows about periodic table, about chemical elements. And first of all, when we talk about nuclear things, we should to say about isotopes.
Why this side, not this flex? Why?
Okay.
Huh? Why?
That isotopes, it's actually the same chemical element, but the only difference is in number of neutrons in the nucleus. It's maybe slight difference, but it's very crucial if we say about nuclear properties,
like this,
different elements.
Not like this.
So on this slide, you see the simplest example. Maybe you know from your school about this, from your college, about hydrogen, deuterium, and tritium.
No need.
And
this is okay, only one, okay.
And there are, you know, approximately 100 different chemical elements, but in the same time, there are more than 2,000 different isotopes. Majority of these isotopes are unstable. It means that after some time, this isotope should to transform in something. And on this slide, you see the most prominent 3 kinds of nuclear decay, so-called alpha, beta, and gamma decay of nucleus for different elements. And first of all, I'd like to say that it's a really miracle because several hundred years ago, alchemistry set about this like miracle, transforming of one element into another one. But nowadays it's just real life. And now I'll demonstrate for you that we can get a lot of different benefits from using of these technologies, of irradiation of different materials or substances, and to use different methods. Of course, I'd like to add very important information. Radiation is not some technologically produced phenomena. Radiation is natural phenomena. Yes, there are natural isotopes and technogenic maybe isotopes. But anyway, anyone from you, from the birth, surrounded by some radiation in our nature. So radiation in this sense, it's some specific of our world, but of course in after discovering of different nuclear phenomena and so on, of course, mankind nowadays can use this technology in broad sense. Of course, I'd like to say about nuclear fission, because we have three kinds of nuclear decay. But when we talk about power generation from nuclear, first of all, we should to say about nuclear fission. So it's just one more phenomena in physics. First of all, for some elements like uranium-235 isotope, it's possible just to go through fission process. After striking with neutron, with some probability, this nucleus can be divided in two parts. You see on this slide, like krypton and barium, two new elements, and several neutrons, secondary neutrons. It's surprisingly some strange maybe phenomena in nuclear physics, but if we can use this reaction in some line, maybe one by one, in this way we can realize releasing of huge energy, and if we manage to use this energy, it will be great for us, but because we can get new very powerful source of energy for different applications. So now I'd like to say about different kind of applications of nuclear technologies and the radiation technologies. Let's start from agriculture. Agriculture, it's very important because anyway, we talk about food, finally. Food for people, for animals, for home animals and so on. And there are plenty of different applications in this field. On this slide, you see applications about plant growth stimulation or inhibition in different situations. So, idea is just to irradiate, for example, seeds by, as usual, gamma rays. What idea? Idea is that from one side, this time of radiation is small enough just to introduce some like radiation effects inside of the seeds. So after this irradiation, all seeds and all fruits or vegetables will be safe for people. But in the same time, irradiation is very harmful for different microorganisms and different bacteria, something like this. And so in this reason, first of all, we can kill different insects, and I'll say about this on the next slides. And in agriculture, it's there are some mechanisms of interaction between radiation and vegetables, for example, fruits and so on. And as a result, after short irradiation, we can get, first of all, huge increase in crop capacity. You see, up to 30% for potatoes, for example. We can accelerate ripening of different vegetables. Of course, it's great because we can get more harvest during the year. And of course, all these technologies, first of all, are intended just to improve productivity maybe in agriculture in some country. The next stage, you know, first of all, pre-sowing stage, pre-sowing irradiation before harvest. But after some time, if we will be so lucky, we will get harvest from the fields. And we will have next problem, how to save this harvest for a long time. In this sense, we can say about inhibition of sprouting. Because for many cultures, on slide you see potatoes, for many cultures, of course, we should to provide special treatment, special conditions of storing for agriculture just to save. But anyway, as usual, it's enough only, I don't know, for several months, 2-3 months maybe. So surprisingly, irradiation can help us in this as well. After short irradiation, we can get huge benefits. Moreover, we have strong advantages in contrast of usual chemical technology. Because chemical technology, you know, it's, as usual, it's harmful one, harmful for people around. For India, I think it's very important because India is one of the most populated country in the world, maybe most populated right now. So food and agriculture is very important field. Actually, I just said about pest extermination. Irradiation can help just to eliminate all small insects in different cultures. And in this way, we can get longer time of storage for transportation for different cultures. And food irradiation, not agriculture, but really food. You see meat, poultry, fish, seafood, first of all, as well as all of us knows that it's actually, especially for fish, for example, for seafood, it's very hard to get some long shelf life for this product because due to different bacteria and so on, actually it can be several days. But anyway, nowadays, of course, we want to get fish in one place and to sell in other country, for example. Of course, we can use usual technologies like freezers, very low temperatures, like different chemical agents. But freezing is very energy consuming technology because it's actually, we need to provide some low temperature just to conserve properties of food. Chemicals as well as it's very like discussable technology because from one side we can store fish or food. From another side, of course, we should to say about possible harmful for people organism. So irradiation of food is widely applied. You see, it's approved more in 69 countries all around the world. And moreover, this technology is not novel one. It's more than 100 years of this technology in the world. So nowadays, by the way, if you will see this sign, this green one in the corner of my slide, it actually means that this product was irradiated, was created in this manner, just to provide high quality of this food for future. How it can be realized in practice? You see on this slide, very simplified picture. Actually, it looks like this one. Some conveyor, some transportation belt. And of course, we can take some box to put, I don't know, vegetables or food in this box. There is no need to use some special package or something like this. And then this belt goes under some like irrigation tube, irrigation facility, and it takes maybe several seconds for different cultures. It will be enough. So that's all. Only several seconds after this food, it's considered as treated and can be delivered for final customer and so on. Of course, you can ask me first of all. You see, most often asked question on this slide. First of all, does irradiation make a food radioactive? Actually, no. I said time of radiation is very short. And it's as safe as using usual X-ray photograph in medicine in your hand. And about creation possible toxic compounds or something like this in the products, of course, it's not as well. So food after this treatment is completely safe. The next area I think known for you, it's very famous one. it's nuclear medicine. Because medicine, you know, it's actually, its area relates for everyone, finally. And we can say about different subtopics here, there. First of all, diagnostics. Diagnostics, just to get some information about our bones, our organism, about human body, about possible diseases. And first of all, it's non-invasive technologies. Of course, we should start from the oldest technology, X-ray radiography. I think anyone gone through this procedure once per year in different countries. More sophisticated, maybe, it's computed tomography. It's not new as well. You see, in 1979, inventors of this technology were granted by Nobel Prize, Hausfield and Cormack, first of all. And it's very prominent in medicine because in this way we can get not single film, single image of some organ or body of some human being, but we can get actually finally three-dimensional model nowadays. It's, of course, it's very valuable source of information for medical doctor. The next kind of diagnostics, radiopharmaceuticals. We will say about this technology later in my presentation. When we just get some like radiopharmaceutical agent, maybe like tablet, but in this way we can visualize some organ for medicine. And example of positron emission tomography, PET scanning, so-called, to use as well as just to visualize some organs in human bodies. The next area, it's not diagnostics, but treatment. Because, okay, for example, we have found something, and the next stage, how we can solve some problems with health by using different technology. First of all, as well as radiopharmaceutical, special radiopharmaceutical agents or tablets, pills, and so on. You see example of treatment of thyroid gland cancer. Idea is just to provide high concentration of some, like iodine 131 in some organ, and in this way, nuclear isotopes just kill damaged cells of body. But idea is that normal tissues will be untouched in this way. The next kind of technology is brachytherapy, to use as well as some isotopes, maybe iodine again, to treat. First of all, in many cases we say about cancers, because cancers different kind of this very hard disease, and actually there are no so many ways just to solve this problem, because you know traditional chemical way is very dangerous as well as, but in this way in many cases we can get high probability to cure this disease for human. Lexel gamma knife is one more example. In this, it's idea not to use special isotopes, but to use special concentration of gamma rays in some point in human body. Idea is the same. Concentrating irradiation by gamma rays can fully destroy possible tumor, for example, but all tissues around will be untouched. But of course, it should be very high precision equipment just to provide this high rate of concentration and treatment. A very important slide nowadays, because you see sterilization of medical devices. Unfortunately, today I have this presentation in online, not in real life by visit in Mumbai, for example. First of all, due to COVID pandemic. And nowadays, this sterilization is very important because a lot of gloves, different medical things, medical devices should be sterilized. In usual way, we should to boil as usual. Should to boil during, I don't know, 10 minutes, but it's long enough, it's very energy consuming technology. We can use radiation sterilization during several seconds, and it will be great. Moreover, as I know, in Russia, Rosatom company, nuclear company, actually has used this technology last year, especially in pandemic situation, just to improve the sterilization of medical devices and sterilization of insects. Because I think in India as well, there are a lot of different insects who are carriers for different diseases. And it's one more technology how to solve problems of possible epidemia of different diseases in tropical climate, first of all. But in the same time, we say about conserving of natural around us and so on. So it's one more way how to realize due to sterilization of insects using radiation. The next element, it's not from medicine, it's not from agriculture, it's actually like from industry and physics, it's research reactors. Research reactors, it's actually special, like on physics course, it's actually maybe small enough, like laboratory equipment, maybe greater in size. And anyway, as usual, research reactors are intended just to provide, you see, different research in nuclear science, material science, and so on, or for production of different radionuclides, of different elements, and so on. And nowadays, all I just said, agriculture, medicine, research reactors, in Rosatom, all these aspects actually are collected together in some idea of centers of nuclear science and technology. Because nowadays, Rosatom state corporation propose two main kind of products abroad: nuclear power plants and centers of nuclear science and technology. So in the heart of this center, as usual, should be some research reactor of different power output and a lot of centers around. You see, nuclear medicine center, radiation material, irradiation center, radiobiology, and as well as education and training. So configuration, of course, should be different in different countries, but nowadays it's a good idea, good model, how to provide all favors of different radiation nuclear technologies for some country in one big product. Okay, the next element, more convenient, I guess, for you and for your country, first of all, it's using nuclear energy to produce electricity, first of all, as a source of energy. You see 5 main kind of generations nowadays. Traditional ones like thermal power plants using coal, gas, hydro, and nuclear, and renewables like wind and solar. So you see name and source of energy, chemical energy or wind energy, and so on. So for nuclear, idea is to use nuclear energy released in the chain reaction or nuclear fuel fission. So very famous layout of nuclear power plant. Idea is to put nuclear fuel inside of special reactor vessel to initialize fission reaction there, and during fission reaction, the fuel get hot. We can just to take this heat from the fuel and to transfer to special steam generation, and finally to boil the water. This water goes to turbine, rotates turbine, and turbine as well as rotates generator. We can get electricity in the grid and to the consumer. So actually it looks like the thermal power plant in this part except of so-called nuclear island. All other parts, turbine, condensers, generators, actually it's a traditional one, like for usual kind of generation. And on the next slides, I briefly just illustrate for you some elements inside of nuclear power plants. So you see nuclear fuel, small pellets from uranium dioxide, like pressed with no cladding. It's actually like ceramics. And it's actually, there is no harm to take this fuel because this uranium, fresh fuel, actually has very low level of radioactivity. It's not so harm for human being. Then from these fuel pellets, we can consist special fuel rods, like stack of these fuel pellets. And these pellets should be put in the special zirconium tube, and this tube will be sealed both ends by welding. So it will be hermetically sealed. And from these fuel rods, we can consist special fuel assembly. Fuel assembly actually it's some unit or to manipulate to handle fuel into a nuclear power plant. And from these fuel assemblies, like from bricks in the constructor, we can collect core, active zone or reactor core for nuclear power plant, for nuclear reactor. So when we say about nuclear fuel, actually, finally, it looks like this picture from the top. And nuclear fuel can be positioned inside of a special reactor vessel with very thick walls, just to prevent pressure, high pressure inside. And we can organize flow of coolant in the VVER reactors, it's water. And we can organize this process of cooling of fuel during operation. And you see, modern reactor vessels are designed for 60 years of operation, with possible extending of lifetime after this. In steam generators, this heat from the fuel, heat of so-called primary circuit, can be transferred to water of a secondary circuit. So actually, it's like cylinder construction vessel with huge number of very thin tubes, heat exchange tubes. You see, more than 11,000 heat exchange tubes. And in this way, we can provide huge surface area, and we can provide huge heat transfer from one circuit to another one. So it's very crucial equipment for nuclear power plant. Altogether, reactor itself and several so-called loops of steam generators and pumps. Actually, it's reactor installation, it's primary circuit. And finally, it's nuclear power plant. Modern nuclear power plant of Russian project of VVER 1200 megawatts of electric power output. So reactor itself is very small part of this construction, because you see special buildings, special protection, and so on. And some key features of nuclear power plant, modern nuclear power plant, are presented on this slide. I'd like to say that nowadays, nuclear power plants are very useful source of energy, electrical energy. And my idea, just to provide electricity, actually 24 hours, 7 days per week. And moreover, for modern reactors, it's designed to provide this mode, operation mode, during 1.5 years. After this time, reactor should be stopped for refueling, for outage, and then after 1 month, this cycle should be started again. So nuclear is my idea to provide stable production of huge amount of electricity in every weather conditions, in every situations with climate, and so on and so on. So the most famous maybe type of Russian reactor technology is VVER. First of all, VVER means power reactor with water. Water used as coolant, as moderator as well. So it's V stands for water in Russian. So VVER 1000 megawatts of electrical power output. You see the first reactor with type from 1980. By the way, this reactor in this year extending of lifetime just started. So 40 years gone for operation for this reactor. And the last VVER 1000 in the Russian Federation was put into operation 3 years ago in Rostov nuclear power plant. Nowadays, we have a more advanced construction, more advanced project of VVER 1200 megawatts, so-called Generation 3+. Moreover, it's the first in the world reactor of this generation. It was connected to the grid 5 years ago. Nowadays, we have totally 4 power units of this project. In India, anyway, I think you know your country is not newcomer in nuclear, because in your country, anyway, there are several heavy water reactors in different places, but not so high power output. And in Kudankulam, Sergei said today in the start of this session about Russian project in India, VVER reactors in Kudankulam nuclear power plant in southern point of your country. Nowadays, 2 units in operation and 2 more under construction. And units number 5 and 6, as I know, under discussion with Rosatom to sign contract. So it's really will be great big power generation facility. Nowadays, you see some geography of Rosatom references of global VVER fleet in different countries all around the world. It's very important because nowadays Russia said that we have experience of operation of our reactor technology in different climates, in different geographical conditions, and so on. And of course, it means that this technology proved safety and high reliability. Of course, when we say about nuclear, we should think about safety in first. There are special protective barriers just to protect actually environment and human around and population around nuclear power plant from possible harmful effect from radiation from fuel. It's fuel matrix, cladding, and you see different stages. Modern nuclear power plants of Russian design are equipped by active and passive systems. Passive means that these systems can operate in total blackout conditions. It means blackout means full absence of power supply on the site. It's very important nowadays because, for example, you saw 1 week ago situation in the United States after very rapid cooling, strong cold in winter in southern states. Of course, it's very big strike in energy system in grid. It's very important for power generation facilities to prevent this situation. And modern nuclear power plants are protected from external and internal factors. On this slide, you see examples. Actually, all possible situations with tornadoes, hurricanes, earthquakes are considered in this project. About environmental impact. On this slide, you see about cleanness, maybe of different kinds of generation, coal, gas, and nuclear. And you see how much energy can be produced from 1 ton or 1,000 cubic meters of gas and so on. And volumes, corresponding volumes of emission of carbon dioxide and mixture of different gases in the atmosphere, so-called greenhouse gases. So nuclear is the best variant if you say about fossil fuels options. And on this slide, all advantages of nuclear power generation just collected together. Nuclear fuel cycle looks like follows nowadays, starting from mining of uranium, producing of fuel, operation, and finally disposal. But in this way, nuclear fuel should be enough, I think, maybe for 100 years. But nowadays, first of all, for India, it's very important idea to use thorium, not uranium, but thorium, because India is the leader in the world if we say about reserves of this element in the ground. It's very interesting, it's very promising technology. And the next step is closed fuel cycle. Idea is not to dispose spent fuel right after operation, several years in a nuclear power plant, but try to get some elements from spent fuel, and in this way we can use this uranium and some elements again and again. But we should provide special technologies. First of all, we say about fast reactors. In India, there is a prototype of breeder reactor in Madras power plant, as I know, under construction. Russian Federation nowadays is a leader in the world if you say about developing of fast reactors. On this slide, you see, first of all, BN 800 megawatts of power output. the most powerful operating fast reactor in the world nowadays. And in the lower part of slide, you see pilot demonstration energy complex with lead reactor breast. Idea is to use fuel in some nuclear power plant and to organize this process of reprocessing in the same site, just to minimize delivery, transportation, and so on. This project is under construction in Siberia now. The next very important area of using nuclear is hydrogen production. Maybe you heard about to use hydrogen as fuel for cars instead of gasoline. But in the same time, hydrogen is very valuable material for industry. It's great, but process of manufacturing of hydrogen, it's very energy consuming. So nowadays there are different projects how to provide actually complex object, to use nuclear reactor, not to provide electricity, but to provide heat, to provide high potential heat to produce hydrogen. And nowadays there are some prototypes in different countries, and I think in near future we will see this technology in real life. The next, I think very important for India as well, is seawater desalination, because nowadays a lot of people all around the world actually needs a source of clean drinking water. In Africa, in different Asia countries, and so on. Of course, there are different technologies, chemical technologies, and so on, how to get clean water. But as well as we talk about energy, how much energy needed to provide some process. We can use nuclear for this task, to solve this desalination. Moreover, in Soviet Union, there was the example of desalination plant with fast reactor, BN350 nuclear reactor. 25 years, this installation was in operation, successful operation, and was shut down only after transformation in Soviet Union in country. But now this idea, I think, will have the second birth maybe, I think in the coming years. The next very interesting point, floating nuclear power plant. Idea is like ship with reactors on board. An idea is just like transportable nuclear power plant. For example, this nuclear power plant can be delivered to some coast to put on the anchor, and I don't know, 10 years, it will be source of electricity for this country nearby. After this ship can be transferred in different place, no problem with spent fuel, with possible radioactive waste, and so on. Only like a big portable source of energy. The first in the world floating nuclear power plant was put into operation actually less than 1 year ago. In Russia, Pevek, it's actually a small city in the north. It's north, very cold region of Russian Federation to provide electricity in the grid. Nuclear powered ships. Of course, maybe you know, there are examples of military applications, first of all, in submarines. Moreover, as I know, in India, there are several nuclear submarines based on Russian projects as well. But we say about civil applications, and on this slide, of course, it's specific for India because you see a lot of ice, it's Arctic actually, and it's icebreakers. Icebreakers because it's actually this example of best maybe using of nuclear advantages for ships. But nevertheless, it's possible to use the same engines for different ships to deliver different goods all around the world, not only for icebreakers. But for icebreakers, it's interesting for us because Russian Federation, it's #1 in this area with biggest nuclear fleet of these icebreakers in the world. And finally, to finalize my today presentation, it's space. It's to use nuclear as source of energy for different spacecrafts. First of all, I'd like to say that this technology, if we say to use nuclear as big battery, big battery to provide power supply on board. This technology was successfully realized, first of all in Soviet Union 30-40 years ago, and several satellites were in the space around us using nuclear power on board. But now we say about constructing special spacecraft just to deliver human on the other planets, first of all on Mars, I guess. And you see some example, unfortunately in Russian, because I'm not managed to find the same in English, but you see, this means nuclear power engine for spacecraft actually. And some idea, reactor in the tail, this is a place to position crew, and of course some construction elements. Nowadays, these nuclear powered spacecrafts in Russian Federation are under development by Roscosmos, Russian space operator, and Rosatom. So actually, I hope we will see some big progress in decade ahead, in years time. And of course, I'd like to finalize my presentation about fusion, because when we say about getting energy, electricity finally, of course, nuclear power plants, it's a current situation and some future perspectives. But of course, I hope that in near time, in 5-10 years, we will see a fusion reactor, first of all, in France, ITER, international project, to start this project start operation, and of course fusion will be great breakthrough in this area. So thank you very much for your attention, because I had only 45 minutes, but actually I tried to provide for you different aspects of using nuclear in different fields. If you will have some questions, please put in the YouTube or maybe in chat in this program, and my colleagues will deliver these answers, these questions for me. So thank you very much.
Thank you very much, Dr. Nahaba, for very interesting lecture and very, very informative. And now we will give floor to our colleagues from Tomsk Polytechnic University, Vera Verkhoturova. Please, Vera. Dr.
Thank you very much, Mr. Fandief. Hello, everybody. Hello, the dear students from Indian colleges. Let me show my presentation today, which is in a continuation of the speech of Professor Nahaba from Moscow University. He gave the perfect brief and review of the peaceful use, energetic and non-energetic application of nuclear technologies. And in my presentation, I would like to focus on the non-energetic application, non-power application of the nuclear and radiation technologies, and not the technology themselves, but the facilities on the base of these technologies. And I would like to show you the opportunities of Russian universities, not only just Tomsk Polytechnic University, where like the example, but I would like to show the opportunities of Russian universities to train the students in the field of nuclear science and technology and radiation technologies. So, first of all, I would like to show you the facilities, nuclear and radiation facilities that are used in the field of nuclear medicine, their common features and their differences. So the biggest, the most important facility and very useful facility for the purposes of nuclear medicine is, of course, nuclear research reactor. So on the picture, you can see the characteristics of the reactor of Tomsk Polytechnic University. And on the photo from the right side, you can see the reactor itself. And I would like to emphasize the fact that now we are the only university in Russia with having operating nuclear research reactor in our structure. And we provide all our international students with the full range of opportunities to be trained at this reactor, both in the field of power applications of nuclear facilities and non-power applications of nuclear facilities. And I would like to say that we have several Indian students among our international students trained at international nuclear programs. In the first lines, you can see the characteristics of our reactor. It is a rather powerful reactor, 6 megawatt, 14 experimental channels, 10 horizontal and 14 vertical, and the applications fields of this reactor. So generally, Professor Nahaba in his speech already said about the main fields of application for any nuclear research facility. And our research facility is the approval of the words of Professor Hakhabov. You see that we use our facility for the development of technologies to obtain new diagnostic and therapeutic radiopharmaceuticals. So it is for sure for the purposes of nuclear medicine. We use our facility to develop the technologies and methods of neutron capture therapy. It is also nuclear medicine to treat different types of cancer, but also we use our nuclear facility for our silicon doping, and this production, this doped silicon is used in the higher current semiconductor technology, radiation material science, and of course to train the students both for as future staff members of NPPs and not only NPPs, cancer hospitals, oncological clinics, etc. But apart from the reactor, one more facility can be used for the purposes of nuclear medicine. So here you can see the name of the facility, cyclotron. On the photo from the right side, you can see our cyclotron, because again, we are the only university in Russia that having not only operating research reactor, but also operating research cyclotron. And in the first lines on the slide, you can see the characteristics of this facility. So what it is, cyclotron is not a nuclear facility, but it is for sure radiation facility. Generally, we can say that it is a big accelerator. So this is a type of accelerating equipment. What are the main differences between the research reactor and cyclotron? The first, and it is obvious even from the photo, the size. The reactor, it is like a small town. It demands the separate campus with a big territory, a complex of the buildings, not only the reactor building, etc. And as I've already said, it is a nuclear facility. Cyclotron is rather big facility, but it does not demand a separate territory. Our cyclotron, which is big enough, is located in one of the university buildings. And again, the second main difference is that it is not nuclear facility, but it is radiation facility. So what are the common features of the research reactor and cyclotron? The common features are that both of these facilities can be used and are used for the purposes of nuclear medicine. Here you can see that the final two lines on the slide. We use our cyclotron to do neutron therapy for oncological diseases, the same as our research reactor. So both facilities can be used for therapy of oncological diseases, different types of therapy, but and to obtain radiopharmaceuticals. So we can produce medical radiopharmaceutical both at the base of nuclear research reactor and at the base of cyclotron. The pharmaceuticals would be different, of course, but the areas of application, as you see, are the same for the reactor and cyclotron. But apart from these medical applications, you can see that we can use this equipment, this facility, also for fundamental studies. We can use it to do activation analysis of the elemental composition of substances and materials, to produce, because it's not only training and research facility, it is a real producing facility, the same as our research reactor. So we can use it to produce polymer membranes and metal nanostructures, and to do radiation testing of products and modification of materials. One more very interesting thing about our cyclotron is that our cyclotron, as you see above, has a channel for neutron therapy in oncology. And very interesting fact that our cyclotron is not fresh, it's not new. It was built and installed in a period of Soviet Union. And from that time till now, this is the only cyclotron in Russia with this channel, this special channel for neutron therapy in oncology. So we are doing the treatment of oncological patients using this neutron therapy channel, and this is the only one in general all around Russia, the only one cyclotron channel, which is also very interesting. So if we use these facilities not only for the purposes of real treatment or production of radiopharmaceuticals, these facilities are a part of university. So that is why all our students, both Russian students and international students, can be trained at the base of these facilities, can do their research at the base of these facilities in the field of nuclear medicine, of course, first of all. And as well as these facilities are also real producing facilities, we can say that from the very beginning, all our students are involved, of course, with some limitations, but they are really involved in the process of real production when we're talking about radiopharmaceuticals production, or in the process of real therapy if we're talking about neutron therapy or neutron capture therapy at the base of our nuclear facility. So one more facility, which is named Betatron, and you can see on the photo that in comparison with two previous facilities, this is a really small facility. It is compact facility. It can be located in any room. It does not demand any special place or even separate campus. This facility is also not nuclear, but radiation facility. It is also a type of accelerators. So it means that this facility is in the same type of the facilities as our cyclotron. Both of them are accelerators, but our cyclotron is a very big accelerator and Betatron compact accelerator. So what is difference in comparison with two previous facilities? If you look at the main application fields, you can see that we can't use Betatrons for the production of radiopharmaceuticals. So this is the main difference are connected to the field of nuclear medicine. But the same as previous facilities, we can use Betatrons to do different nuclear medicine therapy, intraoperative radiation therapy and superficial radiation therapy. So to sum up, these three facilities have some common features and have some differences. The differences are nuclear research reactor is a type of nuclear facility. Cyclotron and Betatron, they are accelerating facilities, not nuclear but radiation facilities. The first two facilities, research reactor and cyclotron, can be used both for production of radiopharmaceuticals and for the treatment of cancer patients. The last facility, Betatron, can't be used to produce radiopharmaceuticals, but on the other hand, it is used successfully to do different types of radiation therapy. So that is why the best way for the university or the country that are developing nuclear medicine technologies to have both all of these facilities, both nuclear and radiation facilities, and in this case, the country, the university, the hospital will be successful in radiopharmaceuticals production and nuclear medicine therapy. So now some details about this facility, their use and the ideas of their usage. On this slide, you can see the trajectory of the development of nuclear medicine technologies in our university. But again, it's just the example, because if the country or university or company starts to develop nuclear medicine technologies, they will go through the same way. Generally, this period takes about 40, 50 years from the start of development till coming to the, you can say, our full cycle of the usage of these technologies. So let's look at the example of our university. More than 40 years ago, in 1980, the first research teams in the field of nuclear medicine were established. Then in 1983, we started to use our cyclotron to do neutron therapy for oncological tumors, and especially tumors of the breast, head, and neck. And as I already said, from that time, the neutron channel that belongs to our cyclotron is the only one in Russia to do these procedures, medical procedures. Then in 1990, the Betatron was developed in our university, and the treatment of superficial malignant neoplasms and skin diseases started. The interesting fact is that Betatron as technology, idea, and then facility was developed by the professors of our university. Now this facility is delivered all around the world, from Great Britain till Indonesia. We are doing the delivery of Betatrons to India. India is one of our main partners in the field of Betatrons developments. So, and the interesting fact that the professors of our university invented this technology and then created the Betatron as facility. So in 1999, also the professors of our university developed a new, absolutely waste-free technology of production molybdenum-99, which is used to produce technetium-99 generators. One of the main things which is used by oncological hospitals and clinics nowadays to do different nuclear medicine procedures for the patients. Before that period, there was just one technology in the world to produce the molybdenum-99, and this technology was connected to the big amount of the waste as a result of the production, and was, we can say, not very ecologically friendly. And one of the professors of our university, the head of radiopharmaceuticals production laboratory, developed waste-free technology, which is worldwide now. And this technology is absolutely eco-friendly, as it is not connected to the waste after the production of this molybdenum. So now in the world, there are just two technologies to produce molybdenum-99 generator isotope, which goes then to technetium-99 generators. Just two technologies in the world, and the founders of one of these technologies, environmental technologies, has been working still in our universities. old professor, world-known professor, and he still teaches the students and helps the students to do their research in the field of production of radiopharmaceuticals. And in 2003, as a result of this development of a waste-free technology of molybdenum-99 production, the development of technology of compact and remotely controlled technetium-99 extraction generators was done. And from that time, we supply and we deliver our generators to 25 medical institutions from Yuzhno-Sakhalinsk till Chelyabinsk in Russia. So, Professor Nakhabov already said about his presentation about the idea of radiopharmaceuticals, what it is, and how we can get these radiopharmaceuticals. And in this slide, you can see that it is just a stereotype that we can use these radiopharmaceuticals only for the needs of oncology. In fact, we can use them not only for the needs of oncological hospitals, but also we see that radiopharmaceuticals produced at the base of nuclear research reactor or cyclotron can be used for the needs of cardiology. They are used to do the diagnostics of heart diseases. They are used, I mean, radiopharmaceuticals to do the diagnostics of kidney diseases, some diagnostic procedures of liver, lungs, etc. So, which means that really now we can use nuclear and radiation technologies not only in the field of power application, but really for the peaceful needs and for the needs of improving the health of the world population. On the photos, on the first photo, which is above, you can see one of the researchers of our research reactor at the final stage of producing technetium-99 generator. On this slide, you can see the main difference between the radiopharmaceuticals produced at the base of nuclear research facility reactor and at the base of cyclotron. So on the first, in the first part of the slide, you see the model of waste-free technology for molybdenum-99 production. And then at the final stage, on the right picture, you can see the result of this technology generator of technetium-99. Then below this model, you see the formulas of production of so-called cyclotron radiopharmaceutical, because as we have already discussed, both of these facilities, reactor, research reactor, and cyclotron, can be used to produce radiopharmaceuticals, but the process of production is different and the radiopharmaceuticals are different. So talking about cyclotron radiopharmaceutical, we see that basically it is thallium-199 and iodine-123. And on the photo from the right side, you can see one of the researchers of our university in the cyclotron complex, who is working at the gold target for thallium-199 production. Well, on this slide, you see the names of the radiopharmaceuticals which were developed at the base of our university and now are used in medical hospitals and medical centers, oncological hospitals and centers. In the center, of course, technetium-99 generators, but not only technetium-90 generators. Here you can see different chloride and somatostatin isotopes production, etc. Well, on this slide, you see the map of the supplying of our Betatrons, as I already said, from the United Kingdom to India and Indonesia. Well, our researchers and engineers have visited your country regularly to assist and to do different technical procedures connected to the Betatrons that were bought by your country. Well, prospects are from the very first sight, we can see that there is no future for nuclear medical technology, because everything has been already done. The nuclear research reactor exists, the cyclotron exists, even the Betatrons were already developed. The process of so-called cyclotron radiopharmaceuticals production has been working successfully. The process of so-called reactor radiopharmaceuticals production is also working successfully. Even the technologies of using the Betatrons in the field of nuclear medicine are already developed. What to do for the future generation of the experts in the field of nuclear medicine? If the student comes to this program, nuclear medicine program, or what he or she will do in the future? What are the prospects? So one of the world-known prospects and the way of development nuclear medicine technologies is named theranostics. As you see, this is the combination of therapy and diagnostics technologies. The idea is, that if the tumor is discovered in the patient, he or she has to face with a lot of physically hard, psychologically hard diagnostic and therapy procedures, which helps the patient to cope with the tumor, but on the other hand, have negative effect on the body in general. So theranostics helps to minimize these negative effects, because the idea of the theranostics is to use together diagnostic and therapeutic products in nuclear medicine based on the target compound labeled with isotopes that was designed to identify these tumor targets and then to do therapy. So it means that we can minimize the number of these procedures, and with the help of one procedure, we can do diagnostics and therapy in the patient. On this slide, on the bottom of the slide, in the right corner, you see the model of the idea of theranostics with the target cell membrane, radionuclide, and vector molecule. So what is already done in this direction? In our university, some radiopharmaceuticals for this targeted delivery were developed. Not only radiopharmaceuticals, but also the methods to use these radionuclides have been developed and optimized. Some are experiments, even with biological objects, were already done. And the final line, a technology to obtain lutetium-177 without a carrier also has been developed, which is also prospective technology in the field of nuclear medicine. Well, the usage of Betatrons in general is also one of the main prospective directions in the field of nuclear medicine. We have already discussed that in comparison with two previous facilities, reactor and cyclotron, we can't use Betatrons to produce radiopharmaceuticals, but on the other hand, we can use them successfully to do some are therapy and treatment procedures. The first one is named intraoperative radiation therapy. So on the photos, you see the process of treatment of the real patients with the use of Betatrons. What is new in the use of Betatrons in this therapy? The final line on the slide is very interesting. You see that 1 minute of such therapy, I mean the therapy with the use of Betatron replaces the 5-week external radiation therapy after surgery. Can you imagine that the patient already coped with a very physically hard surgery? For example, a tumor itself was removed from the patient, but after such surgery, he or she needs to go through a long process of external radiation therapy. Traditionally, it takes about 5 weeks. And we can replace it with just 1 minute of a therapy with the use of Betatron, which is unique characteristic of Betatron. Then one of the main negative characteristic of cancer is that the percentage of relapses usually is very higher. The patient thinks that he or she has been successfully recovered from this disease, has a lot of plans for the future, and suddenly the disease comes back. When we use traditional therapy, the percentage of these relapses, as you see, is about 18%. When we use intraoperative radiation therapy based on Betatron technology, the percentage of local relapses is just 8%, which is very crucial when we're thinking about real people. One more prospective technology is named neutron capture therapy. To develop this technology, you need to have research reactor because this technology is closely connected with the reactor. The idea of the technology is the following. Again, one of the most dangerous cancer tumors now in the world is the tumors of the head and neck, brain tumors, in fact, because very often these tumors are inoperable. You can't treat the patients with a brain tumor. There are several reasons of this fact. First of all, if the tumor locates deeply in the brain, it is not possible to use traditional surgery methods because when you reach the place of the location of this tumor, you can damage the healthy brain substances. And as a result, there will be very serious negative effect to the whole human body. The same reason is why we can't use traditional radiation therapy to treat brain tumors. Again, before reaching the location of the tumor, this radiation therapy can damage the healthy parts of the brain. That is why neutron capture therapy methods were developed. Currently, it is a unique technology for the treatment of inoperable tumors. And thinking about brain tumors, this is the most promising technology with no alternative. Neutron capture therapy technology is very new in the world and in Russia also. Now there are no medical centers that are using this technology. The methods of technology, the basic principles of technology are just being developed. And the staff of our research reactor is working successfully in the field. We have done several tests, not only theoretical calculations, but real tests, also with the use of biological objects. So some testing therapy of the cats and dogs were done at the base of our nuclear research reactor, and it was a very successful therapy. On this slide, on the picture above, you see the model of neutron capture therapy technology. And on the picture below, you see the photo of the application of this technology with a real patient. If you want to develop this technology, on the slide you see the components that the reactor should have to start the work in the field of neutron capture therapy. There should be a separate experimental channel in the reactor for neutron radiation therapy. There should be a complex of the rooms for patient preparation, therapy, observation, etc. There should be special software for therapy planning and some equipment to determine the concentration of isotopes in the blood of the patients. Well, and just one slide about the education opportunities of our university. So we have international master degree program, which is completely in English. So English is the language of training. You do not need to learn Russian before coming to the program, but inside the program as a part of the curriculum, for sure, you will learn Russian at least during the 2 semesters. Here you see the modules or trajectories of training within the program, which is nuclear power engineering, nuclear medicine, and nuclear safety, security, and non-proliferation of nuclear materials. As I already said, the training along all of these trajectories is done at the base of operating facilities, all of them reactors, cyclotrons, betatrons, etc. So welcome to Tomsk. Thank you for your attention.
Okay, dear colleagues. Okay, thank you very much for your very interesting, informative, and useful lectures. And big special thanks for your good, perfect English, Dr. Nahaba and Dr. Verkhoturova. Really, thank you very much. Andrei, what we will do now, we will close this conference, or what?
In my turn, I would like to appreciate our lectures, our speakers, and I would like to say to our students that all the translation will be available on our YouTube channel in the record, and the students can ask their questions under the video in YouTube channel also. And this is the end of our meeting. Thank you very much for your time and for your attention.
Yes. Thank you, Andrei, to you for organizing this very interesting meeting, and salute to Tomsk, our Siberia. Yes.
Thank you.
You know, we have here 30.4 degrees now in Mumbai. You have maybe -20, -25?
You know, no, we have the same degrees, but with opposite, not plus, but minus, -30.
Okay.
But the numbers are the same.
Yes, okay. Thank you. Nice to see you, and see you later. Good luck to you, to all of you. Thank you.
Thank you very much.
Thank you.
Thank you very much.
Nahaba. Thank you. Bye.
Thank you.
Goodbye.
We must see you later.